Hello and welcome back to our series of videos on gas transport. In this video, I'm going to talk about the factors that affect oxygen hemoglobin binding. Okay, so in the last video, I introduced you to this oxygen hemoglobin dissociation curve. Now what I want to tell you is that there are factors that can shift that curve either to the right or to the left. So what you can see here in this graph is in red is the standard curve, and then in blue is our left shifted curve, and in green is our right shifted curve. Okay, so before we talk about the factors that are going to shift our oxygen hemoglobin dissociation curve to the left or to the right, I want you to take a moment to think about what these left or right shifts mean. Okay, so consider these questions here and see if you can kind of verbalize in your head or write down like what it means for that curve to shift to the left or to the right. So go ahead and hit pause and think about that, and we'll come back to it. Okay, so hopefully with a little bit of thinking, you've determined that a left shift indicates that for a given PO2, you're going to have more hemoglobin bound, more oxygen bound to hemoglobin. Okay. So what that means is you're going to have like your hemoglobin binding oxygen more strongly. You're going to have a stronger affinity for oxygen. That's what the left shifted curve means. A right shifted curve is going to be the opposite, right? So for a given PO2, if you compare the values of the red curve versus the green curve, what you see is that with the right shifted curve at a given PO2, you're going to have less oxygen bound to hemoglobin. You're going to be binding oxygen with a lower affinity. You're going to dissociate with oxygen more readily. Okay. All right, so now that we've talked about what it means for our curve to shift left or right, let's think about what circumstances would be happening in the body under which we'd want a right shift to happen, right? So like what would be happening in the body that would make you want to let go of oxygen more readily? What would make you want to have a lower affinity for oxygen if you were hemoglobin? So hit pause if you need to think about that for a minute. Okay, so maybe you figured this out, maybe you didn't, but hopefully it makes sense once I tell you, is that when you have increased metabolism in your body, you're going to want your curve to shift to the right, right? So yeah, if your cells are working a lot, working hard, they're going to want more oxygen. And in a case like that, you're going to want your hemoglobin to have a lower affinity for oxygen so that you can let go of that oxygen, free it up, and make it available to your tissues. Okay, so these are some of the circumstances under which we get a right shift of our curve. Okay, pH. When we metabolize, we create a lower pH, right? We create a lot of acid intermediates in metabolism. So a lower pH is going to cause a rightward shift. Temperature, as we metabolize, we heat up. So at higher temperatures, our curve is going to shift to the right. CO2, okay, when we metabolize, we create higher levels of CO2. So at higher PCO2s, we're going to have a rightward shift, okay? And then finally, this compound 2,3-BPG, which stands for 2,3-bisphosphoglycerate. That's an intermediate in glycolysis. It's also called 2,3-DPG, 2,3-diphosphoglycerate. But in any case, if we're metabolizing a lot, we're going to be making a lot of it, right? So if we have a lot of 2,3-BPG, that is going to shift our curve to the right. All right, so now let's consider the opposite question, right? So a left shift, as you may remember, is going to indicate a higher affinity of hemoglobin for oxygen. We're going to be holding on to our oxygen more strongly. When would you want that to happen? Think about that for a second. Okay, so basically you would want that to happen if you're not metabolizing a lot. Okay, so circumstances, basically it's going to be the same factors that we just talked about, but if they are changing in the other direction, right? So if we had a high pH, that means we're not metabolizing a lot. That's going to cause a left shift. If we have a low temperature, that's indicative of not very much metabolism. That is also going to cause a left shift. Okay. If we have a low PCO2, that's an indicator that we're not metabolizing a lot. That is going to cause a left shift. And then finally, if we have low or no 2,3-BPG, that means we're not metabolizing very much, and we're going to have a left shift in that situation as well. There is one last factor that I want to talk about in which we see a left shift in the hemoglobin binding curve, and that is the case of fetal hemoglobin. So if you look here, you can see that the fetal hemoglobin curve shown in blue is left shifted to normal hemoglobin or maternal hemoglobin, which is shown in red. Okay. And this has a like a functional significance, which is that this allows the fetus to basically, essentially steal oxygen from the mom, right? Since the mother's hemoglobin has a lower affinity for oxygen, it's going to easily give up that oxygen to the fetus, which has a higher affinity for oxygen. Okay, so this is how the fetus gets its oxygen from the mom. And just as a quick little reminder or aside, for those of you who are not that familiar with like how pregnancy works and things. So the maternal and the fetal blood don't mix, okay? So you have blood that is on like a side of the placenta that the mom owns, more or less. You know, it's like an extension of her body. And then you have a side of the placenta that is part, like kind of an extension of the fetus's body. And each of them has their own blood supply. So what's going to happen is that the oxygen here on the maternal side is going to diffuse over through these membranes over to this side where the fetus is. Okay.